Okay, so our focus of the day is going to be the ability to graph the reciprocal functions. So the reciprocal of the sine function is the cosecant function. So I'm putting these two next to each other for a very distinct reason, because I'm going to be able to obtain the cosecant graph from the sine graph. So just to point out for a couple of minutes that what our graph represents from the sine function in kind of an XY table form is that when 0 was the input, 0 was the output. When pi over 2 was the input, 1 was the output. So I'm just taking all the points from our graph and writing them in a table form to help us understand this connection here. Okay? So this is what we know about the sine function in the form of a table. Okay? So the cosecant is the reciprocal of the sine. So, for example, if you know that an angle has a sine of 1/2, what is the cosecant of that same angle? 2, because you would just flip it over. So what I'm going to do is I'm going to create this same table for the cosecant function with the same angles that we used as inputs for the sine function. So you guys told me if there was an angle that produced a sine, the sine of that angle produced the number 1/2, that you know the cosecant of that same angle would produce the number 2 because you just took the result and you flipped it over. Okay? So here's our first angle, 0. When you take the sine of 0, the result is 0. Okay? For that same angle, then, what would be the cosecant of the angle? So you're saying the reciprocal of 0 is, it's undefined. So this would actually be undefined. Okay? At the angle pi over 2, the sine of pi over 2 is 1. The cosecant of that same angle pi over 2 would be what? 1, because the reciprocal of 1 is still just 1. Okay. All right, so what is the cosecant of pi going to be? Undefined, again, because the sine of pi was 0. The cosecant of 3 pi over 2? -1, because it is its own reciprocal. And here, undefined. How do we mark on our graph that values have given us undefined as the answer? What did we do with our tangent graph? Cody? Good. We're going to make those values asymptotes. So I'm going to scale this graph you see here the same as we scaled the sine function graph, but I'm going to graph apparently how the cosecant is supposed to turn out according to our information here. So pi over 2, pi, 3 pi over 2, and 2 pi. All right, so at 0, it's undefined, so that's going to give me, like Cody said, this asymptote. It's also undefined at pi and at 2 pi. Then at pi over 2, it has a point at 1. And at 3 pi over 2, it has a point at -1. I need to know what else is going on between these asymptotes, right? I don't have a full picture. I know there are some asymptotes. These points are in 2 different spots, but I don't get what's happening here. So let's look at the sine graph and see what would happen. Let's say I pick out this point on the sine wave. Okay? It's not exactly at pi over 4. It might look like it here the way I've drawn it, but I'm just going to say I'm picking out the point whose height is 1/2. Fair enough? So there's some angle. I don't know exactly what it is. Actually, I probably can figure out which angle has a sine of 1/2, right? Actually at 30 degrees or so, right? And its sine comes out to be 1/2 at that location. What is the cosecant going to be at that 30-degree location? 2, right? The reciprocal of it is going to be 2. So up here, where on the sine graph it normally hit 1/2, that point is now going to hit up at 2. Okay? Now, there are other points along the sine function that have a sine of 1/2, like right here as well. Right? For us, that would be at like 150 or something like that. That's an angle that also has a sine of 1/2. So its cosecant would be 2. What shape do you think is forming between here? Okay, something similar to a parabola. Is it technically a parabola? it looks like a parabola shape, but what makes it different from a parabola? The asymptotes, right? Does a parabola have an asymptote? No, and that's because it forever gets wider, right? It might take a long time to get as wide as you want it, but it does forever get wider. There's no limitation. Here there are some limitations. So it is similar to a parabola. Okay, that's nice. But it isn't actually that. And so the same thing happens in the negative area, if I can draw. Okay. All right, so this is the cosecant function. What's that? I just noticed that at a certain place between 0 and pi over 2, the sine was 1/2, which means at that same place between 0 and pi over 2, the cosecant would be the reciprocal of 1/2, which would make it 2, because the reciprocal of 1/2 would be 2 over 1. You don't have to know that, though, okay? What you have to know is the shape of the graph. Hannah? No. So I wanted you to see why it works, first of all. But now we're going to find a simple pattern to take a sine graph and turn it into a cosine graph. Now that you know, a cosecant graph. Now that you know a cosecant graph looks like that, what's basically happening to transform this sine function into the cosecant function? Give me some kind of summarizing things. Like if you have a sine, just do this, and then you'll have your cosecant function. Okay. Okay. So she's saying take like half of the period and reflect them. And what's happening at those 0 points in between that aren't part of the above or below area? So what's happening at each of these? Good. So all these points along 0 become the asymptotes. And basically these points stay, but these go the other direction. So I'm not going to memorize where everything on that goes. You guys can. I am going to know how to do this. Okay? So if somebody asks me to graph a cosecant, what am I actually going to graph? The sine function. And then the last thing I'm going to do is I'm going to take all of these points along that midline of the function. And if I want it to be a cosecant, those points are going to become asymptotes because I understand that at some point they would have been undefined. And then wherever the curves are of the sine function, those maximum and minimum values are going to stay, and I'm going to draw those similar to parabola shapes going those opposite directions. Okay? Now, it's not exactly a reflection because it has that asymptote feature, but similar to that. Okay? All right, so the same idea works for any reciprocals. Okay? So now let's try to do it without the chart. If you know that this is a picture of the cosine graph, okay, let's think about what a picture of the secant graph would look like. So somebody tell me where asymptotes would exist. Monet. Yeah, sorry. That's okay. Oh, yeah, thanks. Okay, so what would the period be? 2 pi. Because at this point, it's going to start repeating itself, right? Because the next sine function would create this type of parabola shape, then asymptote. So period is still 2 pi. What is the amplitude of the cosecant function? None. Okay, why does it have no amplitude? Good. It keeps going up, keeps going down. There's no place for us to measure between a maximum and minimum value. Thanks, Monet. All right. So again, we are going to try to do the same idea now that we understand how the idea works and apply it to the cosines relationship with the secant graph. So can somebody tell me where there would be asymptotes for my secant graph based on the behavior of the cosine graph? Min Chao? Good. See the places where the cosine would have been 0? Okay, the places where that function, the points are on like the midline of the function. Those are going to translate to asymptotes when we take our reciprocals. So here we're going to have them at pi over 2 and at 3 pi over 2. All right. Other things? What else did we know when we transformed the sine function into its reciprocal that we could use here? Julia? Okay, good. So the pieces between the asymptotes are going to reflect. So we put an asymptote here and here. So she's saying this was going this direction. We now expect it to go the other direction. Remember those points that were at 1 and -1? 1 and -1 are their own reciprocal, so those points generally stay. So this point will be here. And we'll see that arching that way. Okay. This point that was a maximum right here, that point will stay there. And if we just look at the parent function, we only see half of that. But if we continued the cosine wave, we would see the other half of this and then the asymptote. Okay? And the same idea here. Again, am I going to memorize this as my basic starting place for the secant? No. If somebody wants me to graph a secant, I'm just going to graph a cosine like I know how. And then at the end, I'm going to make these changes to transform it into a secant graph. Okay? So what is the period for the secant graph? 2 pi. Okay, it does all this stuff and then comes back to where it would start repeating itself. And the amplitude? None. Okay. All right, and then we have our tangent and our cotangent. A little bit different because the tangent already has some asymptotes marked on its graph, so we'll deal with that accordingly. So here's the parent function for our tangent, and remember, I know you guys are like, this is more than a period. It is more than a period because here is from 0 to pi, but we don't always like that picture. Sometimes we like between the two asymptotes, so I included a period and a half. So we have the original period plus the part we like to see, and we can see what happens there. Okay, so I will number this graph accordingly. The scale's a little bit different here because what's the normal period for the tangent function? Pi, okay, instead of 2 pi. So, all right. Now we've already determined that places where the original function crosses 0, how does that look for the reciprocal functions graph? Yeah, asymptotes, right? Because the reciprocal of 0 is undefined. So those places where it was hitting 0, those mean asymptotes over here. Now this actually looks promising for the cotangent. Look how nice the asymptotes are of the cotangent. They're actually on 0 and pi. It's kind of like how we wish the tangent function was and why we draw this extra little piece of it, because annoyingly they aren't. All right? Now, this point right here that was at 1, its reciprocal is still 1. So at pi over 4, I still expect this point at positive 1. At 3 pi over 4, there was a point at negative 1, and the reciprocal of negative 1 is still negative 1. So at 3 pi over 4, I expect this point at negative 1. Then the question is, what's happening at pi over 2? So on our original tangent graph, what happens at pi over 2? An asymptote, meaning that the tangent function is undefined at that point. What do we get if we take the reciprocal of something that was undefined? Yeah? Good. It's just going to be on the x-axis because originally this was undefined because the calculation looked like some number over 0, right? If we take that and take the reciprocal of that for the cotangent, it would look like 0 over some number, which isn't undefined. It's actually valued at 0. So what used to be an asymptote becomes 0, okay? For the same reason that the things that are 0 here become asymptotes when you take their reciprocal. Which means the cotangent has a period from 0 to pi, so pi, like you see here, and actually behaves somewhat similar to the tangent in the way it cycles through values. It looks like this. Okay. So what is the amplitude of the cotangent function? Not 1, none. Okay. Because it goes up and down forever. There's no maximum or minimum value. So, again, I don't have to memorize cosecant, secant, or cotangent, but I have to kind of understand what I expect them to look like when I'm done. Instead, I could just graph sine, cosine, or tangent and then transform them. I'll be honest with you, with cosecant and secant, I totally do the sine or cosine graph first, and then at the end I change them. But for cotangent, this is so nice that I happen to just have this memorized in addition to the tangent, and if someone gives me a cotangent to graph, I just start with this. I think it's even nicer than the tangent. The asymptotes are just exactly where I would want them, okay, to shift the period and stuff like that. So I actually start with that. I'm not saying you have to. I'm just saying, I don't know, tangent's not as easy to switch as the others, so it might just be worth knowing what the cotangent is. Okay, up to you. So any questions on what the parent graphs look like? Alex? They don't technically reflect across the y-axis, because here a reflection across the y-axis would keep these asymptotes in the same place, and you don't have that. But visually, yes, the curve appears to go in a direction that would mirror the idea if you had reflected the tangent and then shifted it, or something like that. Okay? Any other questions? All right, so let's do a little. Now remember that tomorrow you guys have a quiz. What is your quiz on? Sine, cosine, tangent, right? So we are not graphing those right now. We are graphing cosecant, secant, and cotangent. However, since we are using a lot of the graphs and then just changing them around, you are going to get some practice with those functions today to make sure you know them. Okay, first graph we're going to do is a cotangent graph. So first decision we need to make, and our decisions can be different. How many people are going to graph the tangent function and then transform it to a cotangent versus how many people are just going to start with the cotangent function and then use that? So how many people are going to start with a tangent function on the graph, finish all the transformations, then transform? How many people are going to start with a cotangent and then do that? Okay, so we'll do it that way up here, but we'll check and make sure that we're the same, okay? All right. So my cotangent function, the first thing I'm going to do is I'm going to figure out the period. So for both tangent and cotangent, the normal period is pi. Is there any transformation up here that's going to adjust the period at all? Minchao? Good. This 1/2 that's in front of the theta or the angle that you would input, right? Is it a horizontal stretch or compression? Stretch, okay? It's really multiplying the period by its reciprocal, which is 2, giving us a new period of 2 pi, okay? So I expect the period of the function to be 2 pi. Therefore, my graph is going to be scaled by whatever that is divided by 4. So 2 pi divided by 4, pi over 2. Okay. So we're going to go ahead and start with our cotangent graph and then just make whatever changes we have to make. Now, given that we've already scaled it according to this 1/2, this other 1/2 is the only other change here. What sort of transformation is it causing? Shannon? Good. A vertical compression, meaning points are moving closer to that midline of the function rather than being pushed far away. So asymptotes for the cotangent function are here and here. Yeah. Okay. There's my asymptotes. So normally my cotangent function goes like this. The only change I'm making is a compression of 1/2 vertically. So this point that is a middle or a point that would be on the midline of the function is going to stay there. And the other points around it are going to be compressed by 1/2. So instead of being 1 unit away, these points will be 1/2 a unit away. Okay. And so then this will be my graph. Minchao? Sure. So if you called this 1 and this 1/2, then you could have just left those points right there. Is this okay with everybody? If you did it the other way, you would have just drawn the original tangent function with the new scale. You would have made those points only 1/2 a unit away, and then you would have turned every 0 into an asymptote and every asymptote into a 0 for the to change the tangent to the cotangent, like we did with the parent functions. Okay. All right, what's the domain of this function? All real numbers except 0, 2 pi. What would be the next one? 4 pi. So if you had to explain the domain, you would say it's all real numbers except, and you'd either make that list, or you'd say even integers or 0 multiples of pi. Okay? You can explain it any of those ways. And what's the range? All real numbers. Good. All right. So the next one is y equals negative 1/2 cosecant of 2 theta. So this is a cosecant graph, but I'm not going to actually create a cosecant graph. What am I actually going to start with? The sine function. So I'm going to graph this as if this were the sine function and do all the things I normally would, and then at the end, I will transform it, okay? So for the sine function, what is the normal period of the function? 2 pi. So normally, our period is 2 pi. We have here this 2 that's going to affect that. It's a horizontal compression. So this is going to get multiplied by the reciprocal of 2, which is 1/2, giving me a period of pi now for this function. So pi. And then I will scale my graph by fourths. So normally the sine function would go here, then up, then back to the midline, then down, and then back to the midline, okay? Assuming that this is 1 and this is negative 1. Those are the normal pattern of points that the sine function would follow. But I have these 2 other transformations here. What 2 other things are taking place? Allison? Good. A reflection, vertical or horizontal? Good. Okay, it's outside of the function, so it's a vertical reflection, meaning this point that used to be at a maximum, it's not going to be there anymore. It's now going to be as like a minimum on the graph, so it's going to get reflected from positive 1 down here to negative 1, and this one that was at negative 1 is going to get reflected up to positive 1. Okay. All right, what's the other change that's taking place? Okay, again, we have that compression of 1/2. So that means the points along the midline will stay, but these maximum and minimum points will be half the distance they were from the midline. So currently they're 1 unit. They're now only going to be half a unit away. Okay. So this is what I get as a period of my sine function for this graph. But I'm not done because I just graphed the sine function. When I look back, my overall goal is to graph cosecant. So how do I take the sine function and then transform it into the cosecant function? Monet? Yes. Now, if this graph had shifted up and down, these would no longer be at 0, but these would still be the place we want to put the asymptotes. Your asymptotes need to be along the points that are on the midline, whether the midline is still at 0 on the x-axis or has been shifted up or down. Okay? So those are my asymptotes. And remember, your maximums and minimums are going to stay. Now, I know the reciprocal of 1/2 is not 2. I get that. But the thing is, you would have taken the reciprocal before you did the multiplying by 1/2 and all of this stuff. So 1 would have remained 1 and then still ended up in the same place after you multiplied it and added something to it. So these points are going to stay, and then we know the shape of the graph, so we'll know what to fill in these areas. And then you can erase the sine graph or just draw it very lightly when you do it, so I know that you know, like, this is not actually part of the graph. Okay. So the period was pi. The amplitude, we already went over for each of these, would be none. Okay. So the only graphs that we've seen that have amplitude are the sine and the cosine function. What about the domain of this function? How would you describe the domain of this function? All real numbers except for Raven? The half pies? Okay. So you would say everyone except, and you could either make a list, negative pi over 2, 0, pi over 2, pi, etc. Could describe it as like the half pies including 0 and, you know, wholes that become, or halves that become wholes, like 2 halves and 4 halves and stuff like that. Okay, so all real numbers except, I'm just going to write it how we said before. But again, if you don't get this, you don't have to. So I would say like k pi over 2, and k could be any integer, right? It could be 0, negative, positive. Jenny? Mm-hmm.
Why you didn't keep the negative 1/2 point, like, for example, percent or more, you didn't
Negative 2.
or like you didn't reflect it over like you did like the AR.
I did. So there's not 2 reflections here, there's 1 reflection. So because I had already reflected, I'm not going to reflect again, I'd be putting it back. So I'm doing all the transformations before I ever turn it into the cosecant. So you don't do the transformations again once you change it into the cosecant because you've already counted for all of them. Shannon? No, I only need to see that you know which direction it's going and you know where it hits for the max or minimum. Okay? All right, what about the range of this function? All of them? Ooh, except 0? Okay, good. There's like this range of numbers that we don't touch, right? So it's all the real numbers except for this little gap in the middle right here between this parabola. That's not really a parabola. I'll use that term loosely, okay? Between this parabola's minimum and this one's maximum, which means it's all the numbers except for those that are between 1/2 and negative 1/2. Okay? Sorry, shouldn't have the equal to's because we actually do get the halves. So, and I'm trying to say except. So, okay. Is this all right, Shannon? I'm not going to put equal to because I'm trying to say these are the exceptions. These are the things that are excluded, but I do actually hit 1/2 and negative 1/2, so I don't want to put equal to 1/2. That means 1/2 is part of the exception that I'm not hitting, and I am hitting it. Min Chao? Yes. You guys get what she's saying? She's going to say y is greater than or equal to 1/2, or y is less than or equal to negative 1/2. Okay, that's the range of numbers. She can say it that way. Other questions? All right, so this says graph y equals the secant of 3 theta. The numbers are messed up. This should say example 9. Yeah, okay. Sorry. Okay, so how many transformations are taking place? 1. And what does the transformation affect? The period of the graph. Okay, it's a horizontal. Is it a horizontal stretch or a horizontal compression? Compression. So it's going to take our normal period, which is 2 pi. We're going to multiply it by 1/3, giving us a period of 2 pi over 3. 2 pi over 3, when you divide that by 4, pi over 6, and then we'll number by pi over 6. So 1 pi over 6, 2 pi over 6, 3 pi over 6, but reduce them, okay? Secant, so we've accounted for the one transformation. Secant is the reciprocal of what graph? Or what function? Cosine. Okay, so normally my cosine function goes like this. Changing the battery. Still keeps stopping. All right. So this is our function, but again, we're going to go through the same changes we took place before. any points that are on the midline, they're on the midline because the cosine was calculated as 0, which means when you take the secant, even if there's other transformations afterwards, it's going to become undefined. So these are marked here. Then any points that were maximums or minimums are going to stay because we would have calculated the cosine. If we change that to the secant, it would stay 1 or negative 1, and then it would have been multiplied by anything or added or subtracted. So it would have ended up in the same spot. But we know the shape of the secant function. So we have this here, and you make sure that Ms. Dahl knows that you understand that that's the graph of the function and not this other portion here. If it's really, really light or something like that, I'll get that you don't think it's part of the graph. Monet? They are if we continued the pattern, because if we continued the pattern, then this would go like this. The next asymptote would be right here at negative pi over 6. Then this one would be here. This would be the next asymptote. Oh, okay. That was the most fun yet. Okay, like this. And this would go like here. No, just follow the directions. Like it'll ask you for maybe 2 periods of the graph or to graph it between 2 specific numbers. Just make sure you follow those directions. Okay? All right, so domain of this graph. All real numbers except every pi over 6? No, skips one everything. You might just want to make the list in this one, huh? Pi over 6, 3 pi over 6, 5 pi over 6, every like odd pi over 6. Okay, you could describe it like that. All right, what about the range of this function? All real numbers. What about this area in here where none of the graph touches? So all real numbers except the y values between 1 and negative 1. Or like Min Chao mentioned, you could say y is greater than or equal to 1 and less than or equal to negative 1. That kind of excludes all that stuff in the middle. Yes. I said you can say all real numbers except the numbers between 1 and negative 1. And if you say that, you're not saying equal to, because we do have 1 and negative 1, so we don't want to make an exception. I said, or you can state the range like Min Chao did, where she just says y is greater than or equal to 1, or it's less than or equal to negative 1. She just says it in 2 inequality statements instead of saying all real numbers except. Shannon? All right, any questions about this? So do you get this idea? Yeah? So this is why I said if we could learn our sine, cosine, tangent function really, really well, then we wouldn't have to worry so much about the reciprocal functions. So they can get more complicated. One more up here that's a little bit more complicated. Just like you saw with your sine graphs, but we can still do, oh, sorry, dangerous, tack going across the room. You were attacked. Get it? Okay. I'm so funny. Okay, so, all right. So let's graph. This is a cosecant, okay? Sorry, Monet. Can we do this first? Okay. So cosecant is related to sine. So let's work on the sine function. This is a sine function with no change in period. So I expect the period to still be 2 pi. Whatever. About done with this. Okay. And we have a horizontal shift, a vertical reflection, and a vertical stretch. That's a lot of stuff going on, right? So normally my sine function starts here and goes through then maximum back, minimum back, okay? But this shift to the right of pi over 2, I'm going to think about the starting point kind of here. And then it would go through these points like so. And this point here, which if I extend this point would be at 5 pi over 2. Okay. All right, so there's the points for my function. I'm trying to walk through a few things before I commit to drawing it, but you don't have to do it this way. Okay? Then there's a reflection and a vertical stretch of 2. With both of those changes, these points are going to stay on the midline of the function. But the reflection has caused things that were maximums to become minimums and minimums to become maximums. And on top of that, now the maximum and minimums are not going to be 1 unit away, but they're going to be 1 times 2, which is 2 units away. Okay? So the reflection and the stretch would remove this point and make it show up down here at negative 2. And it would remove, this point and make it show up here at positive 2. Okay? So that's taking care of those two things. Then the last thing we have to do is move everything up 1. Yes, Monet? Okay. So we're going to move everything up 1. Maybe. Okay. So if we move everything up 1, the midline is going to be like right here. Okay. So this would be here, this would be here, and this would be here. Those are my zeros. This one that was a minimum, remember, it's supposed to be 2 units below the midline. So now that's going to be right here. And this maximum should be 2 units above the midline. That is now going to be right here. So this is our sine function with all of those changes in place. Okay? Now I would change it to a cosecant. Yes?
So if you want us to draw the midline, or...
You don't have to. I'm drawing it there to give me some reference. Minchao? Yes. Because when you think about it, if you were going to do the cosecant calculation, you would be calculating it and it would come up undefined before you ever did any of this other stuff. So it's still going to be undefined at those points. So these points still represent where our asymptotes are. And these points also, you're not going to take their new reciprocal, like, oh, this is at 2, the reciprocal is 1/2, or something like that. You're going to keep it where it is because you would have taken the reciprocal when it was 1 or -1. Then it would have been multiplied by stuff and had stuff added to it. So it would have got shifted to the same place that this point got shifted. Monet, your question?
So the black line of this asymptote, is that just showing us that it's a mid?
Yes. Yes. Okay. So I do that for myself when I shift things up or down because I like to just know, like, oh, it should end up lining centered around this. Because of this right here. Sorry. There. Okay. Is this okay with everybody? You feel like you could transform them? So it's nothing more than this one thing at the end that transforms it from a sine or cosine graph to a secant or cosecant graph. You can do the same for tangent or cotangent, or you could just memorize the cotangent. I don't know. For me, I remember the cotangent better than the tangent function, so that's how I do it, but that doesn't have to be how you choose to do it. Okay?